Our professional development seminar about broadband satellite communication. My co-presenter and I have decided to skip the introductions because we've got too much important stuff to tell you. I'm Alex Hills. I think I know most of you. And Jens Monk is kind of famous. He's chair of the Double E department here and my co-presenter. And I have to say, Jens has been a great collaborator on the work that we're going to be telling you about. Well, satellite communication has quite a history here in Alaska. It all started about 50 years ago with the health aides in our villages. In Alaska villages, the healthcare system depends on health aides who have to be in communication with doctors in regional hospitals. So that communication link was and still is really critical. Back 50, 60 years ago, that communication link was shortwave radio. And you might know that shortwave isn't always that reliable, especially when we have the aurora, especially when we have the northern lights. So back in the 70s, we came into those villages and we put in a whole series of satellite earth stations. This is a 5-meter antenna, and we put those in most all the villages in order to help those health aides with their link to the doctor, but also those same earth stations provided long distance telephone service to the villages and also a television channel. The old timers in the room might remember RatNet, which was this one channel that went out to all the villages. So that's what those village earth stations provided way back decades ago. There's a book about that. It's called Finding Alaska's Villages and Connecting Them. And it's about these two young engineers that went out there and got all that stuff going. And a couple people have asked me to bring some copies of these books in for anybody that might be interested. And so I've done that. And also, while I was at it, a couple of other books, Wi-Fi and the Bad Boys of Radio, which is the one about how we built the first Wi-Fi network in the world at Carnegie Mellon. And also, there's one called Geeks on a Mission, which is about my students who work on projects in developing nations around the world. These books all have a common theme, and I like to say this a lot. A few engineers can make good things happen. And that's really true. It's evident in these books, and it's evident in a lot of other things that go on around here. So decades ago, we got the villages up with, as I said, medical communication, telephone service, television service, but now they need broadband. Just like all of us need broadband. We all use broadband every day, but the folks in the villages have had a problem because their broadband service hasn't really been all that good. So that's been a problem out there for years now. Most of the villages still need better broadband service, but fortunately, technology comes to the rescue because we now have LEO satellites. And so I want to tell you about LEO satellites. A LEO satellite is different from a traditional satellite. A traditional satellite is in what we call geosynchronous or geostationary orbit. So GEO is just the abbreviation for that. And that's a satellite that's in orbit 22,000 miles over the equator, 35,000 kilometers above the equator. That's the altitude at which the satellites goes around the Earth once every 24 hours. That's the same rate at which the Earth rotates on its axis once every 24 hours. So that's why, as seen from the Earth, a geosatellite stays at the same position in the sky. And that's why those Earth stations don't need to track, right? They just sit there in a fixed position because that satellite is geostationary. That's different from a low Earth orbit satellite, which is in much lower orbit, about a few hundred miles or a few hundred kilometers above the Earth's surface. It's about the same altitude as the International Space Station, maybe a little higher. At this altitude, it takes about 90 or 100 minutes to go around once, okay? And also those LEO satellites are not necessarily over the equator. In fact, they're probably not over the equator. They may be in a different kind of an orbit like the one that I show you right here. So to summarize, we've got GEO satellites at 35,000 kilometers altitude over the equator. we've got LEO satellites, and the definition of LEO, generally the definition is an orbit below 2,000 kilometers. And then in between, we've got MEO, medium Earth orbit. I'm not going to be talking about that today because really all the action nowadays is with the low Earth orbit satellites, the ones that are below 2,000 kilometers. Some of you that know about radio engineering may be interested to know what the frequencies are, what the bands are. And there are 4 bands that are of interest for commercial satellites: C, Ku, Ka, and V band. And you're going to see 2 frequencies there for each one, 2 numbers. The first number is the uplink frequency. That's the frequency that a station on the ground uses to transmit to the satellite. And the second number is the downlink. That's the frequency that the satellite uses to transmit back down to the ground. So in the case of C band, the Earth station transmits at 6 gigahertz to the satellite. The satellite transmits at 4 gigahertz back down to the ground. And really, a traditional geosatellite is really nothing more than a repeater in the sky, because a C-band satellite just listens at 6 gigahertz, and whatever it hears, it just retransmits it at 4. So that's how you get this satellite hop, right? So then to summarize on the orbits, the geo orbit is 35,000 plus kilometers above the equator. And at that altitude, for a radio signal to travel all the way up to that high altitude and back down again takes a quarter of a second. It takes about 250 milliseconds, traveling at the speed of light. So we talk about a quarter second per hop. And if you've ever talked on a telephone call that was being routed by satellite, you have probably experienced that satellite delay. In fact, if you've done that, it's really more than a quarter second, because if you ask a question, it's going to take a quarter second to get to the person on the other end, and then it's going to take another quarter second for the answer to come back. So that's a half second for sure. You're going to notice that. And then some phone calls and other circuits are actually routed through multiple satellite hops. So then this can kind of build up after a while. You'll notice the satellite delay if you're watching TV news and you have an anchor person in a studio and a remote correspondent, and they're linked by satellite. So you may notice that from the time the anchor person asks a question until the answer starts to come back, it takes a while, right? And that's going to be a multi-hop situation, so it may take as much as a couple seconds. But that quarter second delay is also a problem for data communication, right? So we always talk about latency in the world of data communication, right? And so latency is a problem. We like that delay or that latency to be as little as possible. Now, low Earth orbit, here we're talking about orbits between 500 and 2,000 kilometers. I said that LEO orbit is below 2,000, and practically speaking, the communication satellites that are in LEO orbit are all above 500. So that's why I say 500 to 2,000. And so at that altitude, the latency is a lot less. It's only roughly between 20 and 50 milliseconds. So that's a lot better. But it takes many LEO satellites to provide service. With a geo satellite, you can get a connection with one satellite, right? Just one satellite sits there and you can connect point A to point B. But with LEO, it's different, because with LEO, if you have a satellite overhead, it's only going to be there for maybe 8 minutes altogether. So if you have a connection that's going through a LEO satellite, it won't take very long. That LEO satellite will fall below the horizon, and you'll need another LEO satellite to come up and pick up the connection. And so that's why a single LEO satellite won't do the job. And in fact, in practice, you need many, many LEO satellites to provide service even to just one location. And as long as you have all those many satellites up there, you are at the same time providing service to, if not the whole world, at least a big part of the world, because they're all up there flying around, providing service everywhere. Some LEO constellations provide service all the way to the poles. And so those constellations do actually provide service everywhere in the world, but other ones don't. So one example of a satellite in polar orbit is the Iridium satellite, the Iridium satellite constellation. Anybody ever heard of Iridium? If you've, and this is not a new system, and it's not a broadband system, but it's one that a lot of people are familiar with because if you use the satellite phone, you're probably on Iridium. If you've used the Garmin InReach, anybody have a Garmin InReach device? People, yep. And so if you use Garmin InReach, you're using the Iridium constellation. And there are also a number of other devices you can get. The Iridium system, and full disclosure, I'm on the board of Iridium. It's been around for more than 20 years, for almost 25 years now. And that's an example of a LEO constellation that's in polar orbit. So we have 6 orbital planes, we call them planes, and then 11 satellites in each orbit. And if you count those orbits from left to right, you'll see that there are 6 of them. So 6 times 11 is 66, and then we have 9 spares that are in orbit. Why do you think we need to have a spare in orbit? It's not all that useful if it's on the ground, right? Because you'd have to launch it. So that's why we have orbits, we have spares that are in what we call a parking orbit at a little bit lower than the operational satellites. And then if there's a problem and we need a spare, then we can move that up to the right position to pick up the load. And actually, this is a very low probability event. It pretty much almost never happens, but if it does happen, those spares are there. One interesting thing is how Iridium got its name. The design was done over 25 years ago, and originally it was a constellation of 77 satellites in the design. And they were looking for a name, so somebody said, well, this is kind of like electrons in an atom, electrons revolving around a nucleus, right? So they went to the periodic table of the elements, and they looked up the element with atomic number 77, and it was iridium. So that seemed like a pretty cool name. But that was with 77 satellites. So then the engineers were still kind of working on the design, and they figured out satellites are expensive, and we really can do the job with only 66 satellites, with only 6 orbits instead of 7 orbits. And so somebody went back to the periodic table. The element was dysprosium. Well, maybe we'll just stick with iridium, you know. So that's how iridium got its name. And as you can see there, the altitude is about 780 kilometers. As far as how the whole world can be covered, here's an animation that shows you the Iridium constellation in operation. The circles represent the coverage areas of each satellite, and so you can see they overlap a little bit, but in total, this polar orbiting constellation does in fact provide coverage everywhere in the world. And we're going to talk about some other kinds of orbits, some other constellations that also provide polar orbit. So that's just an example of low Earth orbit, but it's not about broadband. Iridium provides, as I said, voice service for satellite phones. The Garmin InReach, that's just low speed data. So it's pretty far from broadband. Broadband means high speed data. So now there are a new group of companies that are also using LEO orbits, but this time to provide broadband. And so I want to tell you about a few of those. These are kind of the big players right now. Has anybody ever heard of Starlink? I'm pretty sure you have, yeah, because Starlink has been in the news quite a bit. So Starlink is the first on the list with over 4,000 satellites in orbit. They've already received approval to increase that number to 12,000 satellites, and they also have an additional proposal to go all the way to 42,000 satellites. Pretty big numbers, right? But for now, they've got about 4,000. Another company, how about OneWeb? Have you heard about OneWeb? That's another one that's been in the news because both of these companies are already providing service here in Alaska. OneWeb, counting spares, they have 648 satellites currently in operation, with a proposal to increase that number to over 6,000. So those two companies are operating right now, and they're both providing service here in Alaska. Two more that are working on planning their constellations are Telesat, which is a Canadian company with only 198 satellites. And then, needless to say, Jeff Bezos is in the act here with Amazon, and their project is called Kuiper with over 3,000 satellites. The second two are just in the planning stages, and they both are planning to start launching within the next couple of years. So what I'd like to do now, because they're both in operation and here in Alaska, I'd just like to focus on Starlink and OneWeb and tell you some more details about their systems. So Starlink, actually, I said that LEO satellites are between 500 and 2,000 kilometers. Now Starlink is operating at 4 altitudes between 540 and 570. So they're actually at 540, 550, 560, and 570. At 3 different orbital inclinations. I'll come back and talk about inclinations in just a minute. But in the meantime, OneWeb is at a higher altitude. They're at 12,000 kilometers, and they are actually in polar orbit. So just like the Iridium constellation that I showed you, where they have complete coverage of the entire Earth, OneWeb is also in that kind of an orbit, and that's what we call 90-degree inclination. So here's a little bit, this is pretty much the definition of orbital inclination. If we're looking at the Earth from a distance head on, the equator is that horizontal line, right? The equator looks like a horizontal line, and then the 3 other lines there represent possible satellite orbits. You'll notice that the other 3 lines extend beyond the edge of the Earth. That's because those satellites are at altitude, right? So that's why it's going to extend beyond the edge of the Earth. Orbital inclination is defined as the angle between the equatorial plane and the orbital plane. Angle between the equatorial plane and the orbital plane, which is kind of a 3-dimensional idea, an idea of measuring an angle in 3-dimensional space. But you could also think about it more simply as just the angle between that line that represents the equator and the line that represents the orbit. So, and here I'm showing 53, 70, and 90 degrees. I didn't pick those arbitrarily. Those are the orbital inclinations that Starlink is using. So, as I said, Starlink has over 4,000 satellites in orbit. Right now, they're using orbital inclinations of 53 and 70 degrees. They started off a couple of years ago with a whole constellation of satellites at 53 degrees inclination. Let me just back up. So that 53-degree inclination, that is only going to provide coverage up to about 53 degrees latitude, or maybe a little bit higher because, you know, it doesn't, the signals don't necessarily need to travel straight down, but up to, let's say, 53 to 55 degrees latitude. That doesn't work for Alaska. They were getting a little tip of southeast and maybe the Aleutians, but not most of Alaska. But then, starting about a year ago, Iridium began to launch satellites at 70 degrees. Now that's a lot better. Barrow is a little bit less than 70 degrees, and that's the northernmost tip of Alaska. So those 70-degree orbits are going to cover all of Alaska. And then at first, if you follow the news or follow the people that have been starting to use Starlink service, at first they weren't getting continuous service. So people would say, well, the service is great, but then it drops out, then it comes back. And that's because the constellation was not yet complete. So they'd have a satellite come over, and following my earlier example, maybe there wasn't another satellite to pick up the connection. So that's why they got those dropouts, but that's a lot better now. And as far as I know, the satellite, the constellation is complete and they're not having those problems with dropouts. In the beginning, Starlink announced 100 megabits per second service. That was just kind of their first announcement. The story is actually a lot more complicated because the speed that you experience on Starlink is variable. It's going to bounce up and down depending on how much usage there is of their system at any given moment. So nowadays they're advertising between 50 and 250 megabits per second, but in the real world, from my information, users are actually experiencing speeds between about 20 and 150, just in real life. And latency is roughly in the 20 to 40 millisecond range. Those are pretty good speeds, right? I mean, if you had that service at your home, it would probably be just fine for most things that you want to do. Here's how it works if you want to get Starlink service, and this is pretty appealing to people that maybe are beyond the urban areas or the suburban areas and have a cabin somewhere or out in a village. They don't really have many options, and so this is a way for them to get service that's roughly equivalent to what we can get here in Anchorage, or at least in the same range. So the way it works is with Starlink is you go online and you give them your order, they ship you the equipment, you install it yourself, you turn it on, and it works. And it sounds pretty simple, and from all reports, it really does work that way. It's plug and play. So that's how Starlink works. This is a picture of their very first antenna. Oh, by the way, so they ship you an antenna and the terminal, the electronics, and then you have to install the antenna yourself. They have a number of different mounting brackets that you can use. You could put it on your roof, you could put it on a mast. The main point with Starlink is you'd like to have a clear view of the sky in all directions, or as much as possible. And you'd like to have a clear view down to about 20 degrees elevation. In other words, when that satellite, you'd like to be able to get that satellite 20 degrees above the horizon in all directions. So that's asking a lot. If you have a few trees around, it still might be okay, but ideally you have a clear view of the sky in all directions. And that antenna, that's a 1.2 meter antenna, which has to track the satellite. And the tracking consists of a combination of mechanically steering the satellite, but also electronically steering the beam, because embedded in that dish are a number of small radiating elements, small antennas, right? And if you drive those, I've got my antenna professor here in case I get it wrong. But if you control the phase relationship between those individual elements, you can steer the beam electronically. And so there are two kinds of steering that were used here. One is physically moving the antenna and also using the electronic steering mechanism that I described. Some people are interested in this because they want to be customers. Maybe you have a cabin somewhere, maybe you'd like to have broadband. So the price for service with Starlink is $90 a month. When they originally announced a couple years ago, they started out at $100 a month. Then they bumped it up to $110, and now they're down to $90. And I guess this is just their assessment of what the market will bear, I suppose. In addition to the $90 a month, you also have to pay $599 for that terminal. Like I said, you order the terminal, they ship it, and then you turn it on and you get service. You can get higher speeds if you're a business. So there's a business package that runs at higher speeds for higher prices. And then about a year ago, they announced their RV package. So I guess there are some people that don't have a house anymore. They just travel the country in an RV. And so this is the price. The price for the terminal is the same, but it's a little bit more for the service. Okay, so the other constellation that I wanted to talk about is OneWeb. This is a picture of a OneWeb satellite. And their speed that they offer to a station on the ground is 195 megabits downstream. Oh, by the way, those other speeds I was giving you, it was probably obvious. Those are all downstream services. Downstream, the upstream would be slower. But anyway, OneWeb is 195 over 33. But just like Starlink, it's capacity limited. It depends on how much other traffic is on the network. And also pretty good latencies, 20 to 50 milliseconds. But the big thing about OneWeb is they have a completely different business model than the Starlink business model is direct to consumer. There's no company that's in between, right? It's just, you're just dealing directly with Starlink. OneWeb's business model is they will provide service to what they call enterprise customers, which would be a medium-sized company, a large company, a government agency, a school district, but not to an individual residential consumer. But they'll also provide service to ISPs, to internet service providers. So if you're an internet service provider providing internet within a community, you could use OneWeb to link to the big internet. And so that's the other business model. And in fact, the very first deployment in Alaska was a connection to a tribal internet service provider in the village of Akiak. You all know where Akiak is. It's out on the Kuskokwim River, upriver from Bethel. And so that was their very first deployment, not only in Alaska, that was their very first deployment in the world. So that's another way that a residential consumer could get service, if not directly through Starlink. If you're in a place where there's an ISP that uses OneWeb, then you could get service that way. In other words, you're, as a consumer, you would be dealing with the ISP, then the ISP would in turn be getting service from OneWeb. There isn't too much of that going on in Alaska yet, but there are a few places. And then also, as far as other companies that would be in between the customer and OneWeb, the OneWeb is being represented in Alaska by at least a few companies. The two that I know are Pacific Dataport and ACS. They both represent OneWeb. I showed you a Starlink Earth station. This is a OneWeb Earth station. There are two, these radomes are about this big across, and inside each radome is a parabola that can track. And so the reason you need two of them in this implementation is one of those antennas is moving data from the satellite and the other one is looking for the next satellite. So if you imagine that the one on the left is moving data through the satellite that's overhead right now, and the one on the right is looking for the next satellite to come above the horizon. And then once that satellite is there, then there's a handoff. And now the antenna on the right is moving data, and the one on the left is looking for the next satellite. So that's what at least one version of a OneWeb terminal. They also have a flat panel version that, and I know this is under development, and I'm not sure if it's now being deployed yet, but this flat panel antenna can do everything that I just described in the first antenna. As far as an ISP goes, what they've done in Akiak, the internet service provider actually uses wireless. So it's called a wireless internet service provider, also known as a WISP. And so you have the OneWeb terminal, you have the WISP has a base station, probably located somewhere near the center of the village. And then that has antennas that connect to household antennas or consumer antennas, also flat panel antennas that would be mounted outside the house and pointed back toward that main base station. So that's another way to do things. Now, what I've explained so far is true, but the story has changed just within the past month or two, because what I said quite simply was that Starlink deals direct with the consumer, and that's their business model. and that OneWeb would go through an intermediate like a wireless internet service provider. But now the story has changed a little bit in that there's a recent announcement that Starlink, in addition to what I already told you, is also can deliver something they call a community gateway, which is a much larger facility. You can see 4 radomes there that's capable of moving data at 10 gigabits per second. So that's more than any residents would want, but they are now they can now connect with a local internet service provider. Okay, so that gets back to the same kind of a model that I discussed with OneWeb, except this is moving at much higher data rates, 10 gigabits per second versus about 200 megabits per second. So that's a pretty new development. And their first deployment is here in Alaska, is out on Alaska. Did anybody see this in the paper? It was just in the paper the other day. So they're out on Alaska, and there's an internet service provider, a local ISP out there called Optima ERA. And my best understanding is that the whole point of this is to connect with that local internet service provider. And I'm not sure whether the local ISP uses wireless or cable-based. They may be using a cable-based system for distribution within the village, but in this model, this is how they would get connection back to the internet. Okay, so one question that may be on your mind, because you may have been hearing a lot in the news about the federal government spending lots of money to deploy broadband across Alaska. You've been hearing about this, right? The infrastructure bill and all that. Okay, that money is being used primarily for fiber optic cable, not for LEO satellites. In a few cases, there may be a few exceptional cases where they may fund microwave, but it's mostly about deploying fiber optic cable across the far reaches of Alaska. Sounds pretty challenging, right? That's what the plan is. So a question comes up, so how does LEO satellite fit into all that story? I think we can say that LEO satellite can be deployed very quickly, right? I mean, I've already explained how with Starlink, you just get online, you order the equipment, they send it to you, you set it up, and you're on the air. So LEO satellite, and even with OneWeb, even in that story, it has the advantage of being able to be deployed fairly rapidly. On the other side, optical fiber cable it's capable of some incredible speeds and capacities. And we did a course here about a year ago where we talked about the various broadband technologies. Optical fiber has virtually unlimited capacity, and LEO satellites don't have that. But another thing about these fiber optic cable systems that are being deployed is it's going to take years to get all that out there. And there are some pretty big engineering challenges. I saw a few of you shaking your head when I mentioned about laying fiber optic cable across the far reaches. So it has those challenges, and at the best case, it's going to take years for all that to be deployed. In the meantime, LEO satellites are available right now. And so LEO satellites, I think, are going to be a great option in the near term and maybe the midterm. In the long term, there still might be a question of, do you really need more speed than the LEO is capable of providing? And that'll be a question. So we'll see how it all plays out. But I can say that it's going to take a number of years before those fiber optic systems will be able to be deployed. Okay, so everything I've told you so far about LEOs has been happy, positive, sounds good and wonderful, but there are some issues. There are always issues, right? So one issue is light pollution. When those LEO satellites are in the air, they reflect light from the sun, and that light looks like a bright object in the sky. Here's an example. This is a picture of a set of 60 Starlink satellites that are on their way to orbit. And I'm going to try to put this in motion. There we go. So you can see those satellites. And I've talked to people who said, I got up in the morning and I looked in the sky. And those satellites in that picture, they look to me like the brightest object in the sky. They're really bright. And so it won't surprise you to hear that astronomers are not real happy about this. They're trying to look at some dim object and off in space, and here's this bright object that's right in the way. Now, to Starlink's credit, once those satellites are in orbit, they're not reflecting as much light as what you saw right there. Those satellites were on their way to orbit, but they're still reflecting light and they're still disrupting astronomy. So there's a negotiation going on between the Astronomers Union and Starlink is working to mitigate that reflection problem as much as they can. Another one that I'm sure you've been thinking about this is space debris or space junk, right? With all this stuff flying around up there, what are the chances of a collision? Well, there actually already are some collisions involving very small particles. But the thought that comes to mind is, what are the chances that two substantial objects will collide and throw off debris, and then that debris will strike other objects and you'll get a chain reaction? That's a pretty big concern. It's a critical mass question, right? And it doesn't seem that we're close to that yet, but as more and more satellites are launched, and there are other objects in orbit, not just communication satellites, there are lots of other satellites in low Earth orbit as well. So this is a concern. In fact, the regulators are now requiring that all satellites, once they're no longer useful or usable, that they be deorbited within 5 years. To me, I would have suggested sooner than 5 years. If it's not being used anymore, why not get rid of it right now? But anyway, that's the rule, 5 years. Military activity. Well, I think a lot of this is classified and unknown to me, but there's concern about enemies shooting down our satellites, or as a minimum, putting their own satellites up there, causing radio interference to cause jamming. So I'm sure there's a lot of classified information that DoD has. It's definitely a concern. And then the last one, which is of more immediate concern than space junk and military activity, is radio interference between LEOs and GEOs, and also radio interference between LEOs among the various LEO constellations. There's some concern about radio interference there too. And that's the one that Jens and I have been working on with some colleagues at Carnegie Mellon. So I'll explain a little bit why there's a concern about interference between LEOs and GEOs. The first thing is that the spectrum regulators, in their great wisdom, and we all know they have great wisdom, right? Those are the FCC in the United States, and then at the international level, we have something called the ITU, the International Telecommunication Union, part of the United Nations. Both of them, first of all, they've assigned the LEOs and the GEOs in the same radio spectrum. Now, that might seem a little bit odd at first, because you might think, well, they're each on their own frequency, right? Well, no, not really. If you turn on the radio in your car, you have KFQD is on one frequency, KYAK is on another frequency. That's kind of the standard way that different systems are prevented from interfering with each other. But that's not the case here. The LEOs and the GEOs are all assigned in exactly the same radio spectrum. So you could have a LEO satellite and a GEO satellite operating on exactly the same frequency. So that's the first part of the story. The second part is that the regulators have required that LEOs must accept the burden of not interfering with GEOs. In the terminology, in the parlance, the GEO systems are considered primary, which means they were there first, and so they have priority. And the LEOs came along later. They are secondary and they have to yield to the GEOs. And so the GEOs don't have to change anything about their operation. They just keep on doing what they were doing all along. But the LEOs are required to do whatever they need to do to avoid interfering with the GEOs. And that's a problem that we've been working on. And that's an issue at those three bands that are listed there, KU, KA, and B, because the LEOs and the GEOs are all authorized to operate within those bands. So that's what we've been thinking about. And probably the next thing would be to explain exactly how a LEO could interfere with a GEO. So here we see a picture with a GEO Earth station communicating with the GEO satellite, always in the same direction. And then there's also a LEO constellation, and the LEO with a number of orbits. And here we're showing one LEO orbit with one LEO satellite within that orbit. So now, if that LEO satellite passes in line, passes between the GEO Earth station and its GEO satellite, that's where there is at least the possibility of interference. The way the interference could happen is if the LEO satellite is pointing straight down, pointing its beam down toward the ground, why would it do that? It would be trying to communicate with a LEO Earth station on the ground, right? And if the LEO Earth station is roughly in the same area as that GEO Earth station, and if the transmissions are on the same radio frequency, then there could be a problem. Was that clear? Okay, so that's the situation that we're trying to avoid. Here's another picture, a similar picture. And what we've done here, we've done a thought experiment where we said, okay, here's the GEO and the LEO satellite, and we're going to draw a line between them, and then we're going to extend that line all the way down to the ground. But from the LEO satellite to the ground, we'll put a cone around that line. That cone represents the beam width of the LEO satellite's transmissions, right? That's the radiation from the antenna. And then at the ground, we take that cone and we take the area in which that cone intersects with the ground, and that's the shaded area. It says projected LEO radiation pattern. We're going to call that shaded area a forbidden zone. In other words, we're going to tell the LEO satellite, don't point your beam into that shaded area there. Just point it some other direction, right? And if you point it some other direction, then you're not going to cause an interference problem. So it's all a question of beam steering. When I talking earlier, we were talking about directional antennas and how you point your beam. This is a question of the LEO satellites pointing their beam in a way that won't hit that forbidden zone. And when we've crunched the numbers, we've considered the beam width of the antennas, we've considered the altitudes and so on. So we have the geometry, right? And so we've looked at a number of cases. This is a case, this shows a forbidden zone for a LEO satellite. You can see it there, it's in 53 degrees inclination, and you can see that LEO satellite. And then we looked at a GEO satellite that was way off to the west over the equator, and we did the projection, and we said, well, for that particular GEO satellite and that particular LEO satellite, that's the forbidden zone. But that's just for one GEO satellite. Now, if we repeat the process for all the GEO satellites, and we know where they are, they're all in an arc over the equator. We repeat the process, and now the forbidden zone is much bigger. Now it's all that red. Now that's the forbidden zone. And now we need to look at what happens when that LEO satellite moves. Well, when the LEO satellite moves, the forbidden zone will also move with it, right? So up here on the upper left, the LEO satellite is over the equator. You can see its forbidden zone. Then it moves further north up to about 20 degrees. The forbidden zone moves, and so on. So the instructions to the LEO satellite are, do not point your beam into that forbidden zone, and you have to know where it is as you move. So now you may be wondering, well, what happens if there's a ground station within that, what happens if there's a ground station within that forbidden zone and they need service? What happens to that guy? Well, it's easy, because it won't get service from this satellite, but it gets service from another satellite because there are many LEO satellites in the constellation, right? So it's actually a fairly simple answer. We've run the scenarios for 70 degrees inclination and 90 degrees inclination, but it's all pretty much the same story, which is the forbidden zone moves along with the LEO satellite. And as long as it doesn't aim, and the forbidden zones are pretty small, I mean, they're pretty small compared to where all the customers are that might need service. So that's answering the question about beam steering to avoid interference, except that we've only considered the main beam. We're just talking about pointing the main beam of the LEO satellite. But real life isn't really that simple because there are also side lobes. So now we want to talk about side lobes, and I have to say what a side lobe is. I'm setting things up for Jens now. This picture represents kind of a generic directional antenna. It could be a parabola, it could be a steerable beam, but in general, there's going to be a main lobe and there's going to be side lobes. So now just to explain this, the horizontal axis here, that represents the direction that we're considering relative to straight ahead. So the main beam of the satellite is pointing at 0 degrees, right? And then 5 degrees, that straight ahead, we call that boresight, right? And then relative to that, if we go 5 degrees away from that, 10 degrees away, 15 degrees, and so on. So this represents boresight and then other directions that are off boresight. And then I know that you're not all radio engineers, so I'm just going to say that the vertical axis represents the strength of the signal in that particular direction. If you're a radio engineer, this is directivity measured in dB. Okay, so what we wanted to consider next is we wanted to consider not only interference from the main beam, but also interference from the side lobes. So even if you steer your beam appropriately, side lobes can still cause a problem. This is how that would happen. Here's a LEO satellite that is very appropriately not steering its beam toward that geo earth station. That's a concern. The main beam, you can see the main beam is coming straight down, but then there's also a side lobe off in this other direction, right? So that side lobe, the radiation from that side lobe can be received at the geo earth station, admittedly at a reduced level, right? Not as strong as the main beam. And so we thought about, well, is that a problem or is that not a problem? It's really not a problem as long as you don't have too many LEO satellites up there. But if you've got, remember Starlink with 42,000 satellites? There are some numbers, some projections. Some people think there will be between 50 and 100,000 LEO satellites flying around up there between all the different constellations. So although a little bit of side lobe radiation might not be a problem, if you have tens of thousands of satellites up there, maybe there's a point where that does get to be a problem. And so in terms of the current constellations, our estimates based on published information, our estimates are that in order to avoid this problem for the size of their current constellations, that OneWeb needs to have its maximum side lobe at least 24 dB below the main beam. But that number would change if there are more satellites in the air. And so at this point, I know you've been waiting for my colleague Jens to pick up the ball.
Thank you, Alex.
I'll keep the slides.
Okay, I'll keep. Well, this is just a laser.
Okay, I'll do the slides.
All right. Yeah, can we do the next slide? So I want to talk a little bit about radiation patterns and side lobes and what are the effects of making your antenna dish larger. I mean, so this plot here is of just kind of your standard parabolic dish antenna. at KU band, 12 gigahertz. So a wavelength at 12 gigahertz would be 2.5 centimeters. And so what we've done here is plotted the radiation patterns for a parabolic dish antenna of 0.6, 1.23, and 10 meters. And it turns out that what happens as you allow your dish to get larger physically, the antenna beam becomes more and more focused. Okay, and so you go from your 0.6 meter dish being the solid line here. This is the figure that Alex had previously shown. You increase that to 1.2 meters and you get this dashed line here, and so on. So what we notice is the important thing when we talk about dish size is how big is it in terms of wavelengths. And again, if KU band is 2.5 centimeters, a 0.6 meter dish is going to be 24 wavelengths, and 10 meters is going to be, I think, 400 wavelengths. That is a really, really focused antenna. So, you know, why would you need something that focused? Well, if you're a geostationary Earth station and you have these satellites spaced every 2 degrees, well, you better make sure you're locked on to only one of them. But you can actually be too focused, because in fact, the satellite it's not really geostationary. It actually makes a figure 8 once a day in the sky due to the fact that the Earth kind of does this as it's rotating. So these are what radiation patterns look like for these different dish sizes. And one of the things you'll notice, and maybe it's not apparently obvious, is for these circular parabolic dishes, your first side lobe, when compared to the main beam, is down minus 17 dB. And if you make your dish bigger, your main side lobe is down negative 17 dB. And if you make it even bigger, it's down negative 17 dB. So what happens is your side lobe levels don't change at all. Everything just gets squished into a narrower beam. And as we've already seen for the OneWeb and Starlink, in order for these side lobes, for example, if this antenna happened to be on a satellite, minus 24 dB is right there. So anything above that is a potential problem for the OneWeb satellites. And if we go down minus 33 dB and kind of draw a line across there, you could see that not just the first, but the second, third, even the fourth side lobe could potentially cause interference. So what do we do? Well, we need to figure out how we can reduce the side lobes. And it turns out that a parabolic dish may be a great thing for a ground receiving station where you don't have to move it, or if you do move it, you're anchored to the Earth and not to something very light like a satellite. And for that reason, we may want to consider antenna arrays for your satellite. And antenna arrays have some really great advantages over a parabolic dish that might be the same physical size. So with an array, we have the biggest advantage is the ability to electronically steer your beam without moving your antenna physically. And you can imagine, if you've seen some of the pictures Alex has shown, you know, we see satellites with parabolic dishes on them, but you're probably not rotating the parabolic dish, because if you do that, you're probably going to have to do something to recorrect for, you know, you're going to move the satellite too. So it's kind of out of the question. So you have a lot more flexibility with an antenna array. So what an antenna array is, it's a bunch of antennas that I'm putting in some sort of systematic, orderly fashion. So in this case, I have antennas in a D by D square arrangement. And what I've shown you here is the energy that this thing would project if you were right in front of it. And so this main yellow beam right here would be what we would call the main beam of your antenna. And everything off of that are going to be side lobes, and they are many. And it turns out that we have a lot of control with antenna arrays that we wouldn't have with your standard parabolic dish antenna. We can really shape the beams. We have much more control over the shape of the beam with an antenna array. And one of the things we can do to improve the side load levels is to arrange them basically in a circular way instead of a square array. And it turns out that if you look at the radiation pattern from this circular array and compare it to parabolic dish antenna of the exact same size, they're virtually indistinguishable from each other. But the really cool thing you can do is you can adjust the amplitudes of the currents on each of these elements. So basically, what I've tried to draw here is a kind of a cartoon showing maybe that the antennas at the center here have the most current, and you gradually taper the amplitudes of the currents on your elements as you move out towards the edges. And in this case, we used kind of a Gaussian distribution on this. And so what you see is, if this is the radiation pattern from your square aperture array, if you have it in a circular array, this is your radiation pattern, and you notice it's not surprising, it's kind of circular. Your main beam, you might not notice it from this figure right here, but your main beam gets a little fatter. But what we're going to notice is that first side lobe is lower than it is when you compare it to this case. And then the best case, if the side lobes are the issue, you want to taper the magnitude of your current elements as you move out in this direction. And again, this is I used a Gaussian taper in this, and what you see is your side lobes actually get small very quickly, but your main beam is fatter. So what I want to do now is actually show you plots. So I look at a transect across here, here, and here, and that's going to be my next slide. And so here are the three different cases. So the first case is the square antenna array. And what you notice, that again, this is going to be the solid line. It has the narrowest beam, but its side lobe, the first side lobe is minus 14 dB. So it's not even as good as the circular antenna that we looked at before, the dish antenna. But if you now just look at that second case we consider, which is just like, let's take that square and get rid of all the elements that are outside a certain diameter. And if you do that, you have a radiation pattern that would look identical to a dish antenna of the same size. And your first side lobe is at minus 17 dB. It's right there. But notice we gave up a little bit. If you need a narrow beam, well, you're going to have to make your array a little bit bigger if you need the same narrow beam width as the other case. And the last case is the circular taper, I called it. And your first side lobe in that case is that right there, minus 35 dB. So it's a huge drop off. And if I needed to drop off even more, I could have been more aggressive with the Gaussian taper. So if you like that drop off, at 35 dB, if that's going to work for you, but you need the beam to be narrower, you're just going to have to make your antenna array larger physically. Okay. This is a good example of real engineering where you solve one problem and you create another problem. Whack-a-mole, right? You fix this, you break that. So everything is a compromise. But again, putting your antennas in an array is, going to allow you to steer your beam, you have much more control over the pattern. And if you want to do circular polarization, which is probably a good idea if you're transmitting through the ionosphere, this is a much better way to apply that. I was kind of interested because, Alex, I hadn't ever seen a hybrid antenna where it's part array and part dish. So that was kind of cool.
Yeah.
So you want to go to the last one, Alex?
Yeah, so we're almost out of time. So yeah. let's put these slides up for the Q&A. I'm giving you two references here about describe in much more detail the work that Jens and I have been doing. The first one is about steering the main beam, what I talked about, and the second one is more related to the side lobe issue that Jens talked about. And then I'm also listing the 3 books that I mentioned earlier, which we've got samples up here. So I can just leave this up during the Q&A. I think we may be out of time, but we don't have to leave the room, so we can still keep talking here, right? So that's pretty much what we have to say. Any questions or comments? Yes, sir.
So since we're dealing with LEO satellites, versus GEO satellites, obviously it's moving very fast. I'm very curious, and I think it's an issue that other RF engineers have to take into account, which is how does an antenna or a satellite compensate for the Doppler effect?
Doppler effect.
Yeah. So
Maybe we need to bounce that one to Sean.
good. So it's a, I guess,
This is Sean Fitzpatrick. He's with the Pacific Data Forum.
so I've been in the geo and LEO business for a long time and been working with one of it for about 4 years now. So the question had to do with Doppler and had to do with data streams, right? Because if you're doing synchronous data and you're bouncing that off of a target that's moving, right? If it's moving away, your data is going to appear to slow down. If it's moving closer, it's going to go faster. That can cause problems in synchronous communications, not necessarily a big problem in asynchronous communications today. But one of the ways that they take care of that is simply a data buffer, right? You put a data buffer on the satellite, right? As that frequency shift changes, as it's coming towards the antenna and going away, they simply just use an elastic buffer, right? And so therefore the data coming towards you, right, appears to be at the same rate all the time. The downside to that is it's a buffer. Buffer takes up, uses memory, and it creates delay. So if you're looking for the lowest latency, the larger your buffer is, the more delay you're gonna artificially add to the problem.
Great answer. Thank you. Yes, sir.
And the buffers on board the satellite, not ground station.
Typically on both, but yes. Yeah.
Okay. That one was pretty far down in the weeds.
I should say on
any
satellites
other-
that have onboard processing, on the ones that are purely RF, that's all on the ground.
Any others besides RF engineer? Any other comments?
We got some comments at least from our online
Okay.
friends.
Okay, this is from people out there in YouTube land. One from Sean Fitzpatrick. Thank you, Sean.
Sorry, I was-
Oh, and yeah, Optima ERA is mostly wireless last month. Oh, you're saying they use wireless, not cable based.
For the
Yeah,
last
that was
mile.
when we talked about the Starlink facility in Alaska, and I mentioned Optima ERA as being the local ISP, and I said I didn't know whether they were using wireless, and Sean's contributing that they're using mostly wireless. And great presentation from Kurt. So any others before we adjourn? Yes, ma'am.
What do you think is the part of LEO satellite technology that needs the most research or improvement?
That needs the most research
Or improvement?
or improvement? There's probably different answers to that. We've been focusing on the interference problem, which is kind of the radio engineering problem. And one that we didn't even get to was the LEO to LEO interference. We only talked about LEO to GEO. And then, so to the extent that after we have multiple LEO constellations from different companies, they're obligated not to interfere with each other. And it's still not exactly clear how they're going to do that. It's probably going to require some cooperation, which could be a challenge. So that's one, but a little bit more into your kind of data network thing. You need to give us a little bit of time to think about that. We may actually want to talk with Sean a little bit before he leaves because he's a real satellite expert. But remind me your name?
Maya.
She is interested in from a data network point of view. So we've got all these nodes in the sky, right? So from a kind of from a data network point of view, what are the interesting questions there? So maybe we could stick around a little bit and talk about that a little bit. Any others? I think we took care of everybody that was watching online. Yes, sir.
So with potentially 100,000 lower Leos out there.
Mhm.
It seems like that's awfully dense.
Say what?
Dense in terms of number
Oh,
of
yeah.
square mile,
Mhm. Yeah.
or square kilometers.
Mhm.
Um, why are regulators who tend to be, let's say, conservative, if they're smart at all, why are they thinking in terms of allowing that kind of density? Or is that density?
We already talked about
Am I
how
just
smart
not running
regulators
those numbers
are.
very well in my
Yeah.
head? They're not.
So I put a slide up there for you to look at. Speaking of density, that represents the current Starlink constellation, that's the 4,000. But full disclosure, those satellites are not going to scale, right? So it's not really that bad, but it does kind of emphasize the problem. I don't know if Sean has an opinion. I'm not sure. We talked earlier about how we talked earlier about the space debris problem, about the Kessler syndrome. How bad is it going to be? What needs to be done? I was in Norway doing some lecturing a couple months ago, and some colleagues over there were interested in creating a vacuum. Have you heard about the vacuum cleaner thing to orbit up there and vacuum up all the space junk?
Tough to do
So
that.
I mean, I'm not sure that we have a lot of progress from the public sector to help us with this problem. So it's not a very optimistic answer or a very specific answer, but Sean, do you have any comments?
On the first question regarding the regulators, what we're seeing is that the FCC is taking the position of, I think it is to spur innovation, right? Is to step out of the way, let the innovators figure it out first, and if they can't, and they can't come to agreement, then the regulators are gonna step in and say, here's how it's gonna be done.
This would be on the coordination among the LEO carriers?
Yes, from a frequency standpoint, from a orbital plane standpoint, and those things. There are some recent regulations out about who's going to get access to what frequencies in priority based on where you are in that that LEO distance from Earth.
There's also a company which is a spin-off from Google called Illyria. And one of their missions, they say, is to help the LEO carriers by coordinating their operations, But of course, that requires that the LEO carriers would have to sign up for the program. So, any others? Okay, well, let's stay around and talk about a couple of these issues after we break up. But thanks for your attention. And we do have some books up here for Jeremy and anybody else. I think we probably went off the air a while ago.
So did everybody get the technology?
Before you leave, the password is. Did you inspire that?
No, I